Good afternoon and welcome. It is a beautiful Thursday afternoon. Great time to have a coffee, maybe grab a praline coffee at the Starbucks down at the food court. On here today, I've got Nicholas Carlisle, who's a PhD in engineering student who's going to be discussing his exciting work in the field of microparticle swarms.
G'day, how's it going?
So, to start off, could you give the audience a bit of background information on Nicholas Carlisle?
Oh, on me. So I grew up in the Wairarapa. Came here to Massey quite a few years ago now, did my undergrad here, started a master's, and then went, no, not the fan of this, I'll go do a PhD instead, which is what I'm doing now, about a bit under halfway through it probably at the moment, so yeah.
So, what is your PhD in about? What's the research area, as I briefly introduced it as microparticle swarms?
Yeah, so the overall kind of idea of what I'm trying to look at is reconfigurable systems at the microscale. So in particular, we're looking at microscale robotic swarms, which have a lot of different really awesome potential uses that are starting to be floated around out there in ideas. Most of them towards like kind of biomedical stuff, so ideas on microsurgeries for parts of the body that's hard to get to, targeted drug delivery for, say, cancer treatments and so on. But the overall kind of area that I'm in is still quite young, so there's not much that's been explored there yet, so just kind of, seeing what I can get done with the time I have here.
So you're talking about these micro reconfigurable systems. Could you perhaps break down the concept a bit more lower level for people to understand?
Yeah, so basically manufacturing anything at the microscale or getting stuff to work at the microscale is generally very expensive. Takes a lot of equipment to be able to produce stuff so finely, whereas if we can use some very kind of basic methods for controlling these or adding some energy into this, into a bunch of random particles that are sitting around and get them to do stuff in certain ways, it can be a lot better way of doing it. It can be cheaper, it can be much less time consuming, and it can add a lot more variety for what different microscale tools can actually do.
And what are the size of these particles?
So the ones that I'm working at are 1 micrometer in diameter, polystyrene particles. So that's about a thousandth of a millimeter in size. So very, very tiny. I need a very good microscope to be able to see what I'm doing.
And these overall structures that you make with them, what's the range of size they can be?
It all kind of depends on what type of assembly you're going for. So there's lots of different ways of causing these assemblies to happen, and the different methods can kind of have different impacts on how many particles you can control. So the magnetic swarms, obviously, if you have a big enough magnetic field, you can control hundreds of thousands of these, and you can get quite large ones. I'm using what's called optical tweezers, which is like a highly focused laser beam, and at the focal point, you can do some interesting things to cause some assemblies happening. So mine are a lot smaller than that, but I have very fine control over its movement. So at the moment, I've got mine up to about 100 micrometers squared. So decent size, but yeah, still pretty early on as well. So hopefully we can get much bigger.
And these applications you talk about, let's start off with explaining about this targeted drug delivery idea.
Yeah, so a lot of the stuff to do with that kind of biomedical stuff is mainly at the moment around the magnetic swarms. So the idea for the targeted drug delivery is that you'll get thousands of these little microparticles, and you will either basically coat them in a type of chemo drug. And then instead of injecting chemo into the body where it will go through the entire body and affect your entire body, you can then introduce these little micro robots into the body and control them to go directly to the tumor site or directly to kind of aggregate and crowd around tumour cells so you could directly kind of deliver the drugs right to there, so you don't have to affect the entire body. It can be a lot more targeted and a lot less side effects to the person getting treated.
So this is also like a good alternative to radiotherapy as well.
Yeah, so obviously anyone who knows anyone who's dealt with cancer and chemo, it can be quite a harsh thing for a person to go through. So with this, it would lower the amount of the drug that you need to, first of all, inject into the body, because you can target it directly to where it needs to be, but also you can contain it within that small area so it won't affect the rest of your body and you won't get affected quite as much. But the idea is it'll still have the same kind of effect, if not possibly even better, because if you can control them fine enough, you could get them to physically crowd around and completely cover the cancerous cells. So, yeah, you could get a lot more efficiency with the treatments.
And, like this will obviously minimize the side effects of chemo. Like one of the most notable ones that everyone's familiar with is the hair loss.
Yeah, well, obviously it won't. The drug itself won't affect your entire body, so then a lot of those side effects with like losing weight and appetite and hair and whatnot will hopefully be a lot lowered.
And what was the other example that you brought up?
So the other one that I was talking about was microsurgeries. So one that I've read about in literature at the moment is looking at, say, if you have like a blood clot somewhere in your body or even in your brain, which could cause a stroke. If you have it in a hard-to-get-to-reach place for the current methods for extracting these blood clots, what you could do is create some micro robots that you can use to essentially drill these out, and then you could introduce them to the bloodstream, control where they go into, if the blood clot is in your brain, you could control them through the blood vessels of your brain to get directly to there, so you don't actually have to go into the body and cut anything open. You can just inject them in and they'll travel through the bloodstream, and then you can get them to essentially break apart these blood clots. There's a bunch of other ideas as well. Some around, say, if you cut yourself really badly and you open up an artery, you could use it to do the opposite. You could get them to find their way down to that artery that has been broken further down your arm, say, and you could get it to block that vessel off so that you won't be bleeding out.
And would this also include other kinds of complex internal, like organ surgeries? Like, would it help with? Could it possibly help with heart surgery?
Yeah. Like, basically, if you have fine enough control and you can see what you're doing well enough, which is kind of two of the main problems around this type of technology at the moment. You could probably be able to change it to be useful for whatever test case you need. Like I said before, it's quite young, so these are just kind of the initial ideas that have been thrown around. There's a lot more out there. Like, there's one group in India, I believe, who are using it to try lower the effects of, or lower the reinfection rate of after getting a root canal. So basically, within your tooth, they drill a lot of the affected stuff out, but you have all these little channels within your tooth that you can't get to when you're doing a root canal. So what they'll do is they'll send some magnetic particles into the tooth and then get them to spread out through all these little canals, and then they'll get them to locally vibrate, which causes some heating to occur, and you can use that to then sterilize all the bacteria that's hiding within the tooth that the dentist couldn't get out, and then because they're magnetic particles, you could then accumulate them back into one kind of blob and extract it back out, so you don't have to worry about them staying in the tooth, and you can kind of lower the effect, or lower the likelihood of you introducing another infection.
And so what is your specific twist that you're adding onto it? You made mention of using optical trapping.
Yeah, so at the moment there's a lot of different ways of creating these swarms, and what most ways rely on is to, rather than physically make all these particles form together, you add an energy source that kind of tricks the particles into activating some self-assembly dynamics. So like the magnetic ones, if you put like a rotating field, they'll kind of all come together and aggregate. What I'm looking at is one that uses optical tweezers, like I said before, which is a very highly focused laser. It's used a bit in like chemistry or physics, and starting to get used a little bit in kind of micro robotic fields, which is a very fancy tool where at the focal point, the light is giving off enough kind of energy and force that you can trap particles. And if you do it at a certain place, you can get these particles to accumulate themselves and stick together. So with the types of assemblies I'm looking at are called optical force-induced assemblies. And at the moment, they've only been talked about in literature as, look at this cool thing that happens. And they haven't really looked at what they can do with these or how they can control these assemblies. So I'm looking at what kind of engineering perspective can I bring to these, doing control, automation, and then looking at what these could potentially be useful for.
So when you put this optical trap over your microparticles, what kind of shapes do they make?
Do you mean the assembly?
Yeah, the assembly structure.
So actually the types of assembly that I have are quite interesting in how they react. So they have a couple of certain dynamics that tend to happen each time. So when you trap a particle and take it to air liquid or glass liquid interface, so basically the top surface of the water, the laser kind of scatters throughout the liquid and attracts all the nearby particles. And as they're coming in, it starts to form these kind of concentric circular rings around the central particle that you've trapped. This is kind of known as the kinetic state of assembly. So that's just where they come in, they kind of form these rings. And then over time, they start to kind of rearrange themselves to try lessen the gaps between the particles. And they'll find their way into a much more structured assembly, which is kind of hexagonal in shape. Because all the particles I'm trapping are spherical. So they kind of work their way into almost these kind of hexagon shapes that kind of go outwards.
And when you've got one of these hexagon shapes, can you hypothetically build other things with them?
That's the idea that we're hoping for. So at the moment, as soon as you turn the laser off, everything just falls apart, which is not really ideal. We're hoping to find a way to kind of stick these particles together once they've come together, and then we could potentially use that to be like a micro-manufacturing method. So we could bring particles into a certain place into the assembly, and we could build structures that stay together at the microscale that can be trapped optically wherever, so you can still move them around and have them useful.
It sounds like you're possibly creating the world's smallest Lego set.
That was one idea that I wanted to try play around with. I kind of wanted to do that and then see if I could talk to like the Guinness Book of World Records, but I don't know, maybe I'll try to do that at the end of the PhD, just as a bit of a laugh.
I know getting a Guinness Book of World Records record for the world's smallest Lego set would be pretty amusing.
I believe there actually is one that's pretty small at the moment. I remember seeing one a little while ago, so we'll have to see if I can make it smaller, but I don't know. That might take a bit of design work.
So as you said, you're like one of the first people actually trying to build an application out of this effect that you've observed with the optical trapping. So are there any other groups that are also maybe attempting the same thing that you've observed?
Yeah, so there are a couple of other groups around the world that I've seen using these assemblies. Most of them are coming from more kind of a surface chemistry point of view for them. So like one looked at, person before me in our group looked at changing the surface interactions of the particles and the liquid to see how that affected the assemblies. Another one has looked at using a secondary light source to kind of energize the particles to kind of react in different ways. So at the air-liquid interface, when they turn the secondary light source on, they will kind of snap into their really stable position. And then they notice if they do it at a glass-liquid interface, it kind of spontaneously explodes, and most of the particles go flying outwards. So there's a couple of other groups out there looking at different things, but not so much from the engineering and automation point of view.
And you made mention, what was the material that you were using?
At the moment, it's mainly just plain polystyrene particles. Nothing too fancy, but...
So why exactly are you using polystyrene particles?
That's a good question. So the person who came before me in the group looked at using a few different types of particles for the assemblies. The plain polystyrene they found assembled quite nicely. It also seems to actually be quite a common material to use in these types of applications, especially within microrobotics. Like polystyrene seems to be quite a useful and well-used material for it. So it made quite a lot of sense for us. I had them lying around as well, so I was like, I might as well just use these for now.
And have you considered or reviewed any other kinds of materials?
Yeah, so Susav, who was the one that was working before me, he looked at plain polystyrene, carboxylic coated polystyrene, and then silica as well, looking at essentially what these bring in differently is at the liquid surface, how kind of deep do they float within the water. So that's something called the contact angle. So basically how far up the particle when it's sitting at the surface is actually visible at the top. And so it is looking at what kind of effect that would have on how these particles assemble, because obviously that'll change a couple of different forces that are acting at the microscale. So yeah, I am buying in some new particles at the moment with the carboxylic coating. He actually found that those worked best, but when I came to doing my last lot of experiments, we found that the coating had degraded, so it was working even worse than just the plain polystyrene. The plain polystyrene was probably second best option, not too far behind the carboxyl coated. So for that first lot of experiments, it was kind of the best option I had without buying more in, which is going to be time consuming and a bit expensive, which I'm having to do now.
Are you restricted to operating in water, or can you use different other kinds of liquids?
That is a good question. We had some thoughts around doing, so rather than working at like a liquid air interface, what we were thinking about trying was looking at, say, like a water and oil surface. So basically you can make these little oil films on top of water, and we thought it might be interesting to do stuff there, because then you could develop techniques to work with a lot of kind of surface chemistry point of view. So one of my co-supervisors looks a lot into emulsions, which in chemistry. So if we could find a way to work it at the oil-liquid interface, that would be quite interesting for that. But it's quite difficult to get a nice flat interface. So for all my automation, the less movement at the interface, the better. So I'm at the moment I'm in the process of trying to use a glass liquid. So yeah, we haven't looked too much into the different types of liquid that we could be using in there. But
like hypothetically, if you were to use like a denser liquid, could you make assemblies out of denser particles from denser elements or materials?
So it's not so much. That's not so much a worry with the types of materials. So you can actually optically trap metals. There are some kind of requirements that you have. So to be able to trap something with optical tweezers, it has to be spherical and has to be relatively clear for the trap to actually pass through it. what I've seen in papers a lot is people, rather than using microparticles, they can get like gold and silver nanoparticles, and they found that with that you can actually optically trap them and make similar assemblies. But those are much, much smaller to be able to be trapped. So I don't think changing the fluid would change what you can trap as far as particles go. But yeah, it might be interesting. One thing that I do want to look into is one of our thoughts around my type of assemblies, especially for like a use, would be tissue engineering. So we would have to. I'm interested in looking into using kind of more of a fluid that would be which would allow the cells that you'd be using in the tissue engineering to stay alive. However, there's more like kind of salt content, so I'm not sure exactly how they would trap or make the assemblies in there. I might have to make them first in water, and if I can set them in place, then transfer them. But yeah, there's a couple of different ideas around there.
So wait, maybe I didn't follow exactly. So how is it engineering the tissue specifically?
So the tissue engineering, that's kind of a broad term for basically making man-made tissues. And so one of the things that is done in tissue engineering at the moment is called cell patterning, where you place cells at different spaces from each other, and you can see how they interact with each other based on the spaces and based on the medium that they're in. So that kind of gives you a lot more of an idea around cell interactions with each other, how distance affects it, and you can study a lot more in detail about how all that works. So that in the future we can start making kind of man-made tissues that are very close to, if not the same as what is out there. So say you needed like a skin graft, you might be able to grow skin cells into whatever shape or form you needed that matched with whoever you're trying to give them to. So at the moment, it's trying to understand, to best of my knowledge, it's trying to understand how the cells interact with each other. And so optical tweezers are used in this at the moment, but it's a very slow process because you need to be able to controlling kind of 3 traps at the same time to move like a single cell. Whereas with mine, I could maybe move it with just the one, or if I make a structure that can move bigger clusters of cells, it would be a lot quicker and a lot more efficient to be able to study these cell interactions.
One interesting topic I heard about is the combination of both inorganic and living tissues to create biohybrid structures. Would that be possible with what you're doing?
Yeah, so one of the things that we're actually looking at is kind of functionalizing some DNA strands to act as bonds between particles. We haven't looked too much into that just yet, but yeah, no, that is quite an interesting field. I remember I was over at a conference and someone was talking about they basically made one of these biohybrid robots out of sperm cells because they are very good swimmers and can move around a lot and talk and sense different things around them. And then they put some magnetic particles on there, so then they could kind of control where the sperm cells were swimming, but they still had the functionality that the original cells had. They found that even after the cells died, they could still move them around with a lot of the same kind of pros from having that biological component there.
And maybe just to drop down to a lower level again, maybe we could explain exactly what we mean by biohybrid.
So the biohybrid basically means mixing something biological with something non-biological. So in that case, they got some sperm cells, and then they got some bits of magnetic matter, and kind of found a way to bond the two together. So, and yeah, in simple terms, it's just finding something that's biological and non-biological, mashing them together, and then using that for a task.
So, you've talked about using this optical trapping. Is there any interesting twist you're doing with this optical trapping process yourself, besides experimenting with the interfaces?
The closest, I guess, a little bit. So with optical trapping, there is another very similar process called holographic optical trapping. So that's basically where one laser source is split into many different smaller lasers, and then each of those can form their own traps. So you can control and move around these holographic traps at the same plane that your main one is working at. So what I've done so far is I've been looking at kind of using those two together. So the holographic system, I can control where the position of the swarm is, and I can move it around. So that's in the work I've recently just published in a technically it's published at the moment, I think, in a journal, conference journal. It was kind of my first work towards automation using that. So I make these secondary, kind of smaller secondary assemblies, and then I'll move them to and merge with the main one at the interface. So I'm using that to grow larger and larger assemblies.
And if you're bringing it in together more piecemeal, so to say, that improves the ability to make structures, larger structures.
Yeah, so during the normal assembly process that happens, a lot of particles are actually kind of shot off from the assembly when forces get too high of particles kind of coming in and impacting. The overall energy gets too much and some particles are lost. So if I can bring them in slowly already at the interface, it seems to have a lot better likelihood of being able to hold on to those particles and not others fly off. If you think kind of about what's it called? The little tabletop thing with the four balls, and you pick one up and then it smacks it, and then the other one...
Newton's cradle.
Yeah, Newton's cradle. If you think about it kind of like those, that's what's happening in these assemblies. When particles are kind of bombarding, it gets too much energy and some get shot off, which is kind of what keeps my assemblies quite small. But so if I make smaller ones at the interface and bring them and merge them with the main one at a much smaller momentum, I can get larger assemblies that can stabilize. And then that might turn into using those to, rather than just bring them in and making kind of just a blob assembly, I might be able to get them to come in and join and stay in a certain place and use that to kind of make certain structures that I'm after.
Are there any other kind of forces at play here from a more physics perspective?
There are a lot, and it's really annoying. So obviously from my engineering background, I understand very little about what the forces at play there. But as soon as you get down into the microscale, every force that you can think of doesn't have much of an impact, and there's a lot more different ones at that scale. So basically, at a really small scale, everything is sticky in some way, shape, or form. So there's like electrostatic forces, Van der Waals force, hydrodynamic forces when you're working with liquid, a whole bunch of other things. Like with my assemblies, gravity is not a problem. It's not going to have any effect on my thing overall. Because at that small scale with how light these particles are, there's not enough interaction. So it's a lot more of the kind of surface interactions create all these different really annoying forces that I'm trying to learn how to deal with.
Sounds like you're in need of some help from a physicist.
Yeah, we're looking at that at the moment because so with my particular types of assemblies, a few people have kind of put out ideas on what forces are at play, but no one actually knows yet. So hopefully at some point I can do some proper kind of physics modeling to get a better idea of what's going on there.
And how do you model the physics of it? What tools do you use?
I have no clue at the moment.
Is there maybe some computer simulation packages that you can use?
Yeah. At the moment, from what I can understand, the first slot would be more just studying how the interactions happen. So taking a lot of videos with clear quality, tracking the particles coming in, tracking how they rearrange, calculating like momentums coming in, looking at those particular types of forces due to kind of how they're all sitting, and so on and so forth. Yeah, we're talking with some people in physics at the moment who are quite interested to kind of sink their teeth into this, but at the moment, yeah, it's quite a big unknown for me. Hopefully in a year or two I should know more.
And speaking of, I guess, fundamental sciences, how does chemistry play into all of this?
It's another good question. I'm still learning all of this stuff. I guess that is one of the kind of more annoying parts of working at such a small scale is it's never just a singular discipline, so it's never going to be just engineering for me. There's always going to be physics and chemistry components. So the chemistry can control a lot of the interactions that are happening. So say like changing the viscosity of the water or the surface tension can have quite big effects on the assemblies overall. Also changing, changing like the pH can change how particles interact with each other, and it can make them more sticky or less sticky and so on. So like there's a lot of interactions that at the moment, it's kind of a bit of a black box for me. So I am in the process of starting to learn about all this kind of stuff, but I've still got a few years left before I need to defend this.
So what does the future look like for these micro particle swarms?
The future looks pretty good in general. There's a lot of really exciting work going on all around the world. I'm hoping that my work can be quite a cool contribution. With all of my stuff, I'm kind of looking at, rather than just the kind of ideas that have already been floated around, can we use other methods of making these assemblies to do other tasks? So that would kind of increase and broaden the scope of what people are looking at with these microswarms. Obviously, within the biomedical, there's a lot of interest. A lot of really good researchers have big groups working on this, and there's a lot of research getting pumped out at the moment, which is mind-blowing, some of the stuff that they can do with it. So yeah, hopefully my work can kind of make its own mark on this kind of unknown way of doing these assemblies, at least as far as engineers are concerned. So hopefully I can inspire some people to look at other methods of making them and then try get different ideas of what can we actually do with them.
And are there like some future applications that are a bit more conceptual at this stage that, maybe something cool for people to think about?
Well, at the moment would be micro-manufacturing. So making, say, functional tools at the microscale. So say in a little solution of water, you have these particles that you don't want in there. You could make these little contraptions that could kind of surround them, close them off, so you can kind of isolate them by themselves and then remove them from the sample. Yeah, it's probably about it as far as the ideas I have at the moment.
So the world's smallest pair of tweezers or grippers.
Yeah, essentially, something like that.
But for, I guess, manipulating things that the optical trapper would otherwise not be able to do so, or do so efficiently.
Yeah, exactly.
And you talked about it doing drug delivery, but could it also perhaps... Could you perhaps also make micromechanisms which are capable of maybe taking samples from within the body, maybe from more of a diagnostics point of view rather than treatment?
Yeah, I mean, that's always an option. I think that's probably a bit further off. It's a bit easier to use them to place stuff somewhere rather than to retrieve stuff at the moment. But that is definitely a possibility in the future. I have seen some people discuss stuff like that for doing like microbiopsies. So you could send them to a place where you think might be cancerous and get them to take a very small sample, or use them as some form of sensing. So you can you might be able to functionalize them in some way that they react to different environments. So you could put them in a certain environment around a cancer cell, and if you know that, say it'll change, the cancerous cell will change the pH of the local environment. You could drive them along there and see if that interaction happens, and if it does, that might be a good indication that a proper biopsy might be needed, or something else, some other form of treatment might be needed later.
So cancer changes the pH of its surrounding area?
That's just kind of one example. I haven't looked into all that too much. I know that cancerous cells do change the properties around them, but I'm not entirely sure what you would be sensing with it yet, but I do know people have talked about the possibilities of doing something like that.
And one thing I often think about when it comes to like microfabrication is the microelectronics space, so, semiconductors, all that stuff.
Yeah.
Can your particle assembly like this possibly assist in this area?
Actually, there is one group who used a very similar kind of accumulation method to, rather than accumulating pixels of little particles, they used it to form a kind of crystalline matter. So they had some solution that had bits of different materials in it, and then when they trapped at the interface, it started accumulating certain bits out, and it was making these little crystalline structures. So there could be some possibility for that in the future. I have also heard of people with microswarms, the magnetic ones, they actually use them to repair microcircuits. So you could make like a little, similar to an ant bridge, to kind of bridge a gap across a little bit of trace that's broken. So there are definitely many possible applications that these swarms could go into.
I mean, how small could these ant bridges be?
I don't know. I mean, you could do them with nanoparticles, so they could get really, really fine. Yeah.
Because I know that when you're operating, like when you're getting down to a very fine nanoscale, it actually gets pretty hard for clear signals to be sent along, because there's interference from what is it? You get interference. You run into problems with fundamental physics, basically.
Which everything seems to at that scale.
Which start to really have a big impact on how your electronic signals are sent throughout your circuitry.
Yeah, so at the moment, that group was just looking at repairing kind of circuits that aren't quite that small. So they just had some little, very tiny flexible circuits, like kind of, I think they might have been like a millimeter or two in size. And so then they were making some fairly large, or comparatively large, little amp bridges to span the gap. But yeah.
So when you will eventually move on to actually creating your own structures, what would be like one of the first things that you want to make? Like functional mechanisms.
Functional mechanisms would probably be a little gripper. So to do that, I'd need to find some way of making a hinge. So like I was saying before, if you think about a little structure that had kind of two semicircles and a hinge in the middle, if you could create it so that the other end of it was open and that hinge actually worked functionally, you could open it up and go around something that you don't want in there, or something that you want to isolate to test later. You could then get it to close and lock itself off around it. And because all of the stuff is at a top interface, it's not going to push down into the liquid. So if you do that, then you've securely grabbed onto some structure that you wouldn't be able to optically trap, whether it's like a biological material and the optical trapping might cause heating and kill the cell, or whether it's just a really weird shape or a material that doesn't trap well. You could use that for that. So that's kind of the first idea that I want to try out.
So when you're talking about a hinge, obviously you don't mean a traditional hinge like with a pin in it. This would have to be some kind of compliant mechanism. right?
Yeah, so we'd have to find some way of bonding particles together so that there's still a little bit of flexibility and give in there, and then you'd want just a really thin section of it that you could then use to kind of be a functional hinge. So kind of like if you were 3D printing a structure that has a hinge on it, it's just a very fine layer around. So it doesn't provide much resistance, but it kind of holds everything from falling apart. So that's kind of what the idea would be at the moment.
And how exactly do you get something to have a little bit of give in it versus not? I know you said that physics and stuff is very complicated at that scale, but usually people they'll associate all thin materials with being somewhat flexible if they're made thin enough. So how is flexibility different in this scale?
Just trying to think. So at the scale, it's quite hard to actually get stuff flexing at that scale. So obviously with how small it is, if we started looking at a larger scale and it was made up of all these small things, it would look quite flexible to us, to the naked eye. But at that scale, having particles that close together, it's quite hard to get them to move around and flex. So it'd be more probably, rather than looking at a flexible material for what we're making it out of, it would be looking at how can we make more kind of flexible bonds between them. So something that has a little bit of give and a little bit of movement, we could then make kind of a flexible structure with it.
And so you need to have it basically on like a particle by particle level, them to be able to kind of slide and shift around one another. Whereas I suppose if you're at the larger scale, each individual particle's not actually moving that much.
Yeah, exactly.
It's kind of like how we're sitting here on the Earth, which is obviously a sphere. Ooh, controversial. No, it's not controversial in science. But it, obviously it will look much flatter down at the level that we're at.
Yeah, exactly. It's hard to kind of think about the different scales without actually looking at it. Provides quite an interesting challenge, which I'm looking forward to tackling. We've got some ideas around it, but we have to wait and see how well they work out.
And so what does the end of your research project look like to you?
Well, at the moment, it's just kind of speculation, obviously. I'm hoping that by the end of it, I've been able to probably make these micro-manufactured structures. I have some ideas around how I want to do it, and I think that would be achievable. Basically producing some functional tools at this microscale. That would be, I think, pretty good for me overall. And maybe kind of pushing that towards potential applications. So identifying a few ideas of, once I have it working, this tool could be used for this reason, or you could make it this way. I'd be pretty happy with if I got to there.
And do you have any planned like conferences that you're eyeing up?
So we're hoping the next place I'm going to be submitting to is hopefully RA Letters, or Robotics and Automation Letters. I'm just starting that work now, so hopefully it goes well enough. If I do manage to get it submitted there, I will be able to go to one of the conferences called IROS or ICRA. Those are probably two of the biggest engineering conferences in the world. I think the next... so the ICRA is going to be in Yokohama early February, which probably when I'm going to be submitting it. So we'd be hoping for IROS, which would be Abu Dhabi, which going to a conference of that size is a really cool experience. I recently went to IROS in Detroit, which I believe I can't even remember what it stands for now, but it was really cool being there. There was, I think, about 2,000 works being presented there, and some really, really interesting stuff over a huge range of different fields within engineering.
Now, are there any subject areas that I haven't asked you about that you would like to touch on?
Not really. I think we covered most things.
Okay. It sounds like that we've reached the end of this discussion. Now, if anybody wants to contact you about potential collaborations or just a discussion of your research, or maybe they've got some kind of interest, how would they reach out to you?
Probably the easiest way to do it would be to search up the Massey Microrobotics Lab. There is a webpage for that that I believe has all my contact details on it. Or go talk to my supervisor, Ebu. Or come find me. I'm in the Reddit building. I'm normally wandering around, sometimes at the pool table.
Or maybe for people who are a bit further away, maybe some kind of email?
Yeah, so my Massey email is n.carlisle, so n.carlisle@massey.ac.nz. Yeah, I'll see your email if you send something there, and I'll try to get back to you.
All right. It was a pleasure having you here, Nick.
Yeah, well, thanks for having me. It was an interesting time having a good chat.
And if you feel like you could come here into the studio and have a chat about your field of research, give me a contact at martinallen111@gmail.com, and I can organise a slot to have you on here. It is currently 2:48 in the afternoon on a beautiful first day of November, and the next song coming up is Keep Me Afloat by Esby.